Hi everybody, we're going to continue to talk about vectors by talking about magnitude and direction. To help us think about that, I want to do a quick simulation. As the figure moves from point to point, it goes through a distance. For vectors, we call this distance the magnitude. We also see that there's a direction to the movement. In our first movement, the cat moved down. Let's look at a second direction. This time the cat's moving up, and again, we could talk about how far up does the cat move. This gives us both the second magnitude, but also a different direction. When we look at quantifying magnitude and direction, it helps to have a scale. We can turn on a grid to see how far the character moved. We can also include an axis with numbers. This will help us put our vectors in standard form before we calculate the magnitude and direction. Before we get started, let's talk about a little bit of notation. We already said the length of a vector is called the magnitude. Magnitude can be denoted with double bars or single bars around the vector. Given a vector v in standard form ab, we have that the magnitude is the square root of a squared plus b squared. Magnitude is just another application of the Pythagorean theorem. If I have the vector u equal to ab, then I can form a triangle with a base a height b, and the hypotenuse will stand for the magnitude. So just like we would find the hypotenuse by finding the square root of a squared plus b squared, we find the magnitude of the vector by finding the square root of a squared plus b squared. Vectors are equal when they have the same magnitude and direction. Don't be fooled by vectors that have the same magnitude. Having the same magnitude does not make the vectors equal. They also have to have the same direction. We know from study of trigonometry that we could have the same magnitude in every quadrant of our plane. So we have to make sure that our direction is also the same before we say that two vectors are equal. Direction is measured by the angle formed between the vector and the x-axis. So if we call our angle theta, we'll find that tangent of theta is b over a. To find theta, we'll take the tan inverse of b over a. When finding the direction of a vector, we tend to give the angle as a positive number. So if you get a negative, we'll convert it into a positive angle. So let's go back to our previous example of our two vectors. Our initial movement went from the point -4, 1 down to the point 2, -7. Then from 2, -7, it went up to the point 6, -1. We can label these two vectors as u and v. To start, we'll put u in standard form. We'll subtract the ending point 2 from the beginning point -4, and then the ending point -7 from the beginning point of 1. This puts our vector in standard form of 6, -8. Now that we have u as 6, -8, we can find the magnitude. We'll say the magnitude is the square root of 6 squared plus -8 squared. 6 squared is 36, -8 squared is 64, 36 and 64 gives me 100. The square root of 100 comes out to be 10. Now that I know the magnitude, we can look for the direction. To find the direction, I'll draw a quick triangle. We'll draw the horizontal length of 6 and the vertical length of -8. Then to find our angle theta, we do the tan inverse of opposite over adjacent. So we have the opposite -8 over the adjacent of 6. When we put that in the calculator, it gives us -53.13. To switch the negative from a positive, I add 360, and it says my direction is 306.87 degrees. Let's repeat the process for our second vector. We went from 2, -7 up to 6, -1. In standard form, our vector v is 6 minus 2, then -1 minus -7. 6 minus 2 gives us 4, -1 minus -7 gives us a positive 6. Again, once we have our vector in standard form, we're ready to find the magnitude. We'll write the magnitude of v is the square root of 4 squared plus 6 squared. That gives us the square root of 16 plus 36, which is the square root of 52. To find the direction, I'm once again going to draw a triangle. This time, I go to the right 4 and up 6. To find the tan inverse, I take the opposite 6 over the adjacent 4, and I put it in my calculator. This gives us an angle of approximately 56.31 degrees. To finish up our talk about magnitude and the direction of vectors, we need to add a quick note about quadrants. As you find the direction of a vector, remember to look at the quadrant of the terminal point. Take, for example, the vector w that's equal to -4, -4. If I take the tan inverse of -4 over -4, that's just the tan inverse of 1, which is 45 degrees. But if we think about 45 degrees, it's in quadrant 1. But our vector has a terminal point in quadrant 3. So we need to look for an angle in quadrant 3 that has a reference angle of 45 degrees. To get that angle, I add 45 to 180, which gives me 225. Remember, when you're using the inverse trig function, it's always going to pop up answers that are in quadrant 1 or in quadrant 4. Anytime your vector is in quadrant 2 or quadrant 3, you're going to need to use reference angles to find the actual direction of the vector.